Somewhere out there right now, a rock the size of Manhattan is tumbling through the darkness between Mars and Jupiter. It weighs nearly 7 billion metric tons. It has been circling the sun, silently and without purpose, for longer than any continent on Earth has existed, longer than any ocean has held water, longer than any living thing has drawn breath. And in the year 2001, a spacecraft built by human hands touched its surface, the first time in the entire history of our species that anything from our world had ever landed on an asteroid. That asteroid's name is Eros. Most people have never heard of it. Most people, if asked to name an asteroid, would say something about the one that killed the dinosaurs. Or maybe they would mention the asteroid belt, that ring of debris between Mars and Jupiter that science fiction likes to portray as a dense, chaotic minefield of tumbling rocks. But the reality of the asteroid belt is nothing like that. If you stood on any given asteroid in the main belt and looked around, you would not see another asteroid. The nearest one would be millions of kilometers away. The belt is not crowded, it is lonely. And the rocks that populate it are not dramatic, flashy objects. They are old, they are cold, they are dark. And they have been drifting through space, unchanged since before the Earth existed. Eros is one of those rocks. But it is not just any rock. It is a near-Earth asteroid, meaning its orbit brings it dangerously close to our planet. Close enough, in fact, that astronomers in the late 1800s used it to calculate the distance from the Earth to the Sun, one of the most important measurements in the history of science. Close enough that it was once considered a potential impact threat. Close enough that when NASA decided to attempt the seemingly impossible, to send a robot across hundreds of millions of miles of vacuum and gently land it on a tumbling, irregularly shaped, gravity-starved world no one had ever seen up close. Eros was the target they chose. The mission was called Near Shoemaker, Near-Earth Asteroid Rendezvous. It launched in 1996, arrived at Eros in the year 2000, and spent an entire year circling the asteroid, photographing every inch of its potato-shaped body, measuring its gravity, analyzing its composition, mapping its geology in extraordinary detail. Then, on February 12, 2001, mission controllers did something the spacecraft was never designed to do. They brought it down, slowly, carefully, gently descending toward a surface no human eye had ever seen up close. The spacecraft touched down at a speed of roughly 1.5 meters per second, slower than a casual stroll, and it survived. It kept transmitting from the surface for 16 more days. The first machine from Earth to rest on the surface of an asteroid. But the landing was not the most important part of this story. What the mission revealed was, because Eros turned out to be something nobody expected, it was ancient, older than any rock on Earth, older than the Earth itself. Its surface was covered in massive boulders, some the size of football fields, that seemed to defy explanation. Its craters were oddly shallow, as if something had been filling them in from below, some invisible hand smoothing over the scars of ancient impacts. Its density suggested it was not a solid rock at all, but a fractured, shattered body, broken on the inside but still holding together, a pile of interlocking fragments held in shape by nothing more than the faintest whisper of its own gravity. And scattered across its surface were strange, flat regions filled with fine dust that looked almost like ponds, smooth, featureless, eerily out of place on a world where everything else was jagged and rough and ancient. There is something profoundly unsettling about this image. A world so broken it should have fallen apart billions of years ago. A world so old it predates every geological feature on Earth. A world so close to us that its orbit crosses paths with our own, carrying within it enough mass and energy to end civilization if it ever arrived at the wrong place at the wrong time. And we sent a machine to land on it. We touched it, we studied it, and what we learned raised more questions than it answered. By the end of tonight, you are going to understand what Eros truly is, how we reached it, what we found there, and why this battered, ancient rock drifting silently through space may hold the key to understanding not only where our solar system came from, but whether anything like us could ever survive what comes next. This is the story of the first asteroid humanity ever landed on, and it is far stranger, far more beautiful, and far more terrifying than you might expect. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. The story of Eros begins not in space, but in a dome-roofed observatory in Berlin. On a cold August night in 1898, an astronomer named Gustav Witt was not looking for anything in particular that evening. He was photographing a different asteroid, a well-known body in the main belt, when something caught his eye on the photographic plate. A faint streak of light where there should have been a dot. Something had moved during the long exposure. Something was out there, drifting against the fixed pattern of the stars, and it was not supposed to be. Witt investigated. He went back to the plate. He measured the streak, its length, its direction, its position relative to the known stars. He compared it to star catalogues and to the predicted positions of known asteroids. None of them matched. This was something new. He calculated a preliminary orbit, working through the mathematics by hand, and what he found startled him. This was not a main belt asteroid, safely tucked between Mars and Jupiter, like the hundreds already catalogued at the time. This object's orbit crossed inside the orbit of Mars. It came closer to the Sun than Mars ever did, and at certain points in its long elliptical journey around the Sun, it came startlingly close to Earth. He named it Eros, after the Greek god of love. It was only the 433rd asteroid ever discovered. But it was the first one ever found, whose orbit brought it into Earth's neighborhood. That distinction alone made it extraordinary. But what made Eros historically significant? What turned it from a mere curiosity into one of the most important objects in the entire history of observational astronomy was what happened next. To understand why Eros mattered so deeply to astronomers in the early 20th century, you need to understand a problem that sounds almost absurd today. They did not know how far away the Sun was. Not precisely. They had rough estimates, they had ranges, but the exact distance from the Earth to the Sun, a fundamental number called the astronomical unit, the yardstick on which every other measurement in the solar system depends, had never been pinned down with real accuracy, and without that number, the entire scale of the solar system was uncertain. The size of Mars, the distance to Jupiter, the diameter of Saturn's rings, the orbital speed of Mercury. All of these calculations relied on knowing the astronomical unit, and the astronomical unit was fuzzy. Previous attempts to measure it had used transits of Venus, rare events when Venus passes directly between the Earth and the Sun, appearing as a tiny black dot crossing the solar disk. By observing these transits from widely separated locations on Earth, and measuring the slight difference in the time and position of the transit, astronomers could use parallax to calculate the distance to Venus, and from that, the distance to the Sun. But transits of Venus are extremely rare. They occur in pairs separated by 8 years, with gaps of more than a century between pairs. The last pair before Witt's discovery had occurred in 1874 and 1882, and the results had been disappointing. The measurements were imprecise, the calculations plagued by systematic errors, and the final values disagreed with each other by troubling margins. The astronomical unit remained uncertain. Eros changed everything, because Eros came so close to Earth. Within about 22 million kilometers at its nearest approach, astronomers realized they could use the same parallax technique, but with a much closer target, yielding far more precise results. By observing Eros from different observatories around the world at the same time, and measuring the tiny shift in its apparent position against the background stars, they could calculate its distance. And from its distance, using Kepler's laws of planetary motion, they could work out the distance to the Sun with unprecedented accuracy. In 1901, Eros made a particularly close approach to Earth, and observatories around the globe coordinated a massive campaign to observe it. It was one of the first great international scientific collaborations in the history of astronomy. Telescopes in Europe, South Africa, Australia, and the Americas all pointed at the same tiny dot of light, night after night, gathering data with painstaking care. The results, when compiled and analyzed over the following years, gave the most accurate value of the astronomical unit that had ever been achieved. For the first time in history, humanity really knew, with precision, how big its own solar system was. And the answer had come from a tumbling rock named after a god of love. But knowing how far away Eros was only raised a deeper question. What was it? What was it made of? How large was it really? And perhaps, most urgently, was it dangerous? Throughout the 20th century, astronomers studied Eros with increasingly powerful telescopes and increasingly sophisticated techniques. They measured its brightness as it rotated, tracking the way its reflected light rose and fell over a period of about 5 hours and 16 minutes, one full spin on its axis. From those brightness variations, they could deduce something remarkable. Eros was not round, it was elongated, lopsided, shaped roughly like a shoe or a peanut or a misshapen potato, depending on who was describing it and how generous they were feeling about potatoes. Later, radar observations from the Arecibo and Goldstone radio telescopes confirmed this, bouncing microwave signals off the asteroid's surface and reconstructing its three-dimensional shape from the reflections. The picture that emerged was of a body approximately 34 kilometers long, 11 kilometers wide, and 11 kilometers thick. Massive by human standards. To put that in perspective, if you set Eros down in the middle of a major city, say New York, it would stretch from the southern tip of Manhattan all the way to the northern edge of the Bronx. It would cover the entire borough of Manhattan, and then some, a mountainous, cratered, airless rock sitting where skyscrapers used to be, its highest ridges towering kilometers above the surrounding terrain. This is not a small pebble drifting harmlessly through space. This is a world, and here is what made Eros particularly compelling to planetary scientists. Spectroscopic analysis, the study of the specific wavelengths of light reflected from its surface, revealed that Eros belongs to a class of asteroids called S-types, or silicaceous asteroids. These are rocky bodies made primarily of silicate minerals, olivine, pyroxene, feldspar, mixed with metallic iron and nickel. S-type asteroids are the most common type in the inner asteroid belt, and they are of enormous scientific interest because they appear to be closely related to a class of meteorites that regularly fall to Earth, called ordinary chondrites. These meteorites are among the most primitive materials in the entire solar system. They contain chondrules, tiny, glassy spheres of silicate mineral that formed in the solar nebula itself, the swirling disk of gas and dust that surrounded the young sun more than 4.5 billion years ago. Ordinary chondrites have remained largely unchanged since those earliest days. They are time capsules from creation. Holding one in your hand is as close as you can come to touching the raw material from which every planet, every moon, every grain of sand on every beach, and every atom in your body was ultimately made. But there was a problem, a nagging, frustrating, decades-old problem that refused to go away, no matter how much data accumulated, no matter how many papers were published, no matter how many conferences debated it. When astronomers compared the spectra of S-type asteroids like Eros to the spectra of ordinary chondrites measured in the laboratory, they did not match. They were close, tantalizingly close, but not right. The asteroid's surfaces appeared redder, with subtly different absorption features. The spectral signature was off. Something was different. This discrepancy haunted planetary science for the better part of 3 decades. Either S-type asteroids were not actually the parent bodies of ordinary chondrites, which would upend a foundational assumption about where meteorites come from and what they tell us about the solar system, or something was happening to the surfaces of these asteroids that was altering their optical appearance without changing their underlying composition. Something was putting a mask on the asteroids, disguising their true nature. Scientists called this hypothetical process space weathering, and for years it remained exactly that, a hypothesis, an educated guess, a placeholder for ignorance. The idea behind space weathering was straightforward, even if the details were murky. An asteroid's surface is exposed to the harsh environment of space for billions of years. Solar wind, a constant stream of charged particles from the sun, bombards the surface. Micrometeorites, some no larger than grains of sand, slam into the surface at speeds of tens of kilometers per second, vaporizing on impact and creating tiny melt deposits. cosmic rays penetrate the outermost layers. Over time, these processes could alter the optical properties of the surface minerals, darkening them, reddening them, creating nanometer-thin coatings of metallic iron that change the way light is reflected. The fresh, unweathered interior of an asteroid, which is what you see when a chunk breaks off and falls to Earth as a meteorite, would look different from the weathered surface that telescopes observe from hundreds of millions of kilometers away. The meteorites would show the true composition. The asteroid surfaces would show a disguise. It was an elegant hypothesis. It made physical sense, but it had never been tested. No one had ever been close enough to an S-type asteroid to measure its composition directly, bypassing the ambiguous spectral data. No one had ever gotten close enough to see whether the surface composition matched the meteorites beneath the mask. It was against this backdrop, this intersection of deep historical significance, genuine unresolved scientific mystery, and the tantalizing possibility that a single mission could crack a puzzle that had stumped planetary science for a generation, that NASA conceived of a mission unlike anything attempted before. Not a flyby, not a distant observation, a rendezvous, a long, intimate, year-long encounter with a single asteroid, getting close enough to study it in ways that telescopes on Earth never could. The mission concept emerged in the late 1980s and early 1990s, during a period of enormous ambition and also enormous constraint at NASA. The agency had just endured the Challenger disaster in 1986 and was struggling to rebuild public trust while simultaneously trying to reinvent its approach to planetary exploration. The old model, massive, multi-billion-dollar flagship missions that took decades to develop and carried dozens of instruments, and had the bureaucratic inertia of an aircraft carrier, was being challenged by a new philosophy. The phrase that captured it was faster, better, cheaper. Build smaller spacecraft, launch more often, accept some risk, focus each mission on a specific set of questions, get results quickly and affordably. The NEAR mission became one of the very first test cases for this new philosophy. It was selected as the inaugural mission in NASA's Discovery program, a new line of competitively selected, cost-capped planetary science missions designed to do focused, high-quality science at a fraction of the traditional price. The principal investigator was Andrew Cheng, a physicist at the Johns Hopkins University Applied Physics Laboratory, known universally as APL, in Laurel, Maryland. Cheng and his team designed a spacecraft that was elegant in its simplicity. No lander, no sample return capsule, no complex deployable structures, just a suite of carefully chosen instruments, a camera, spectrometers, a magnetometer, a laser altimeter, mounted on a compact, solar-powered body weighing about 800 kilograms at launch. The total mission cost, including the spacecraft, the instruments, the launch vehicle, and mission operations, was approximately $223 million. That sounds like a lot until you compare it to the Cassini-Huygens mission to Saturn, which launched just 1 year later and cost more than $3.4 billion. Near Shoemaker was lean, it was focused, and it had one job: get to Eros, orbit it, study it more thoroughly than any small body in the solar system had ever been studied, and answer the questions that had been piling up for decades. Each of those instruments had been chosen to address a specific aspect of the Eros puzzle. The multispectral imager, a camera capable of taking pictures through multiple color filters, would map the surface in visible and near-infrared light, revealing variations in color and composition that the human eye alone could never detect. The near-infrared spectrometer would measure the reflected sunlight from the surface at hundreds of individual wavelengths, producing spectral fingerprints of the minerals present: olivine, pyroxene, feldspar, metallic iron, and, crucially, comparing them to the spectra of ordinary chondrite meteorites measured in laboratories on Earth. This was the instrument that would put the space weathering hypothesis to the test. The X-ray and gamma-ray spectrometers would measure the elemental composition of the surface by detecting the characteristic X-rays and gamma rays emitted when the surface atoms are excited by solar, radiation, and cosmic rays. These instruments could determine the abundances of key elements: silicon, magnesium, iron, aluminum, calcium, sulfur, potassium, with a precision impossible to achieve from Earth-based telescopes. The laser rangefinder, a device that fired short pulses of laser light at the surface and measured the time it took for the reflections to return, would map the three-dimensional shape of Eros with extraordinary accuracy, building a topographic model precise to within a few meters. And the magnetometer would search for any magnetic field, even an extremely faint one, that might reveal whether Eros had ever been part of a larger, differentiated body with a molten iron core, or whether it had always been a cold, undifferentiated assemblage of primitive material. It is worth pausing here to note the spacecraft's name, because it carries a weight that goes beyond bureaucratic nomenclature. The mission was originally called simply Near Earth Asteroid Rendezvous, but in March of 2000, just 1 month after the spacecraft arrived at Eros, it was renamed Near Shoemaker in honor of Eugene Merle Shoemaker, the legendary planetary geologist who had died in a car accident in Australia in 1997. Shoemaker had spent his career proving that asteroid and comet impacts were not just relics of the distant past but ongoing processes that had shaped, and continued to shape, every solid body in the solar system. He had founded the field of impact geology. He had trained Apollo astronauts to read lunar geology. He had co-discovered Comet Shoemaker-Levy 9, which slammed into Jupiter in 1994 in one of the most spectacular astronomical events ever witnessed. He had dreamed, his entire life, of going to space himself, but a medical condition had disqualified him from the astronaut program. Naming the spacecraft after him was a tribute, and in a strange, poetic twist, when Near Shoemaker eventually landed on Eros, it carried with it a small capsule containing some of Eugene Shoemaker's ashes. The man who had spent his life studying impacts from afar finally came to rest on the surface of an asteroid. It was, in every sense that mattered, a homecoming. The spacecraft launched on February 17, 1996, aboard a Delta II rocket from Cape Canaveral, Florida. It rose into the pre-dawn sky on a column of flame and noise, arcing eastward over the Atlantic, climbing through the atmosphere, shedding its boosters, and finally igniting its upper stage to fling the small probe out of Earth orbit and onto an interplanetary trajectory. It was the first spacecraft ever launched with the explicit primary goal of orbiting an asteroid. Others had visited asteroids in passing. Galileo had flown by Gaspra and Ida on its way to Jupiter, but Near Shoemaker was going to stay. It was going to match orbits. It was going to settle in. And it was going to watch, and measure, and record everything it could. The journey would take 4 years, including a gravity assist flyby of Earth itself in January of 1998, which bent the spacecraft's trajectory and boosted its speed, sending it on a long arc toward Eros. Along the way, in June of 1997, it flew past another asteroid, Mathilde, a large, dark, carbon-rich body in the main belt about 53 kilometers across. The Mathilde flyby was a bonus, an opportunistic encounter made possible by the spacecraft's trajectory, and it produced its own surprise. Mathilde turned out to be astonishingly porous. Its density was so low, only about 1.3 grams per cubic centimeter, less than half the density of typical rock, that it was essentially more empty space than solid matter. It was a flying sponge, a rubble pile so loosely packed that you could almost imagine reaching your hand into it and pulling out a fistful of gravel. That brief encounter with Mathilde offered an unsettling preview of the surprises that lay ahead at Eros, and a hint that asteroids, as a class, were far stranger and far more structurally bizarre than anyone had imagined. But then came disaster. On December 20th, 1998, Near Shoemaker was supposed to fire its main engine and enter orbit around Eros. This was the most critical maneuver of the entire mission, the orbit insertion burn. If it failed, the spacecraft would sail past the asteroid at high speed, and the mission would effectively be over. There would not be enough fuel to turn around and try again. Controllers at APL sent the command. The engine fired, and then, within seconds, something went wrong. The spacecraft's onboard computer detected an anomaly. A thruster was firing in an unexpected sequence. The software, following its programmed safety protocols, aborted the main engine burn. The spacecraft tumbled. It lost its orientation. It lost contact with Earth. For 27 agonizing hours, the mission team at APL had no idea whether Near Shoemaker was alive or dead. They sent commands, they listened for signals, they waited. The tension in the control room was suffocating. Months of planning, years of effort, hundreds of millions of dollars. All of it hanging on whether a small machine, tumbling in the void hundreds of millions of kilometers away, could save itself. When they finally re-established contact, they found the spacecraft had managed to stabilize itself using its backup attitude control system, but it had missed its rendezvous with Eros. The carefully planned orbit insertion had failed. The asteroid was receding into the distance, pulling away at a speed the spacecraft could not match. The moment had passed, the window had closed. The mission appeared to be over before it had truly begun. But here is where human ingenuity, the stubborn, creative, sometimes desperate ingenuity of people who refuse to accept that a problem is unsolvable, turned catastrophe into triumph. The navigation team, led by Robert Farquhar, the mission's legendary flight director, realized that if they adjusted the spacecraft's trajectory with a carefully designed series of engine burns, they could catch up with Eros, but it would take an extra 13 months. Instead of arriving in January of 1999 as originally planned, they would arrive in February of 2000. It meant rewriting the entire mission timeline. It meant burning precious fuel that had been allocated for orbital maneuvers. It meant extending operations, paying staff, keeping the deep space network antennas pointed at a spacecraft that was, for the moment, not doing anything at all. But it was possible, and so they did it. On February 14th, 2000, Valentine's Day, a fitting date for a rendezvous with a body named after the god of love, Near Shoemaker fired its engines one final time and slipped into orbit around 433 Eros. It was the first spacecraft in history to orbit an asteroid. Nothing like it had ever been attempted, let alone achieved. The journey from Earth had taken 4 years and covered more than 3 billion kilometers, and now, finally, Near Shoemaker was there, circling a body so small that its gravity was barely a rounding error, roughly 1/1000th the strength of Earth's. At the surface of Eros, a person who weighs 80 kilograms on Earth would weigh less than 30 grams. You could jump and never come back down. You could throw a baseball and watch it leave the asteroid entirely, sailing off into the void of interplanetary space, never to return. The escape velocity at the surface of Eros, the speed you need to reach in order to leave its gravitational influence forever, is approximately 10 meters per second. That is the speed of a brisk jog. This was the world Near Shoemaker had come to study, a world where the familiar rules of gravity are barely suggestions, where boulders the size of apartment buildings sit on surfaces so weakly held that a firm push could dislodge them for eternity, where the horizon curves so sharply that you can see it bend, and the sky takes up most of your view, and the ground feels like it is falling away from you in every direction. And what the spacecraft found there, in the high-resolution images, in the spectrometer readings, in the laser altimetry data, in the gravity field measurements, would challenge assumptions that had stood for decades, resolve a mystery that had nagged planetary science since the 1970s, and open new questions that scientists are still wrestling with a quarter century later. But here is the problem. Nobody knew what an asteroid looked like up close. Not really. There had been flybies, Gaspra, Ida, Mathilde, but those were brief, fleeting encounters, snapshots taken at high speed. Nobody had ever lingered. Nobody had ever had the time to look carefully, to study the surface in detail, to build up a comprehensive picture of what an asteroid actually is. All the theories, all the models, all the assumptions, they had been built on remote observations and educated guesses. And now, for the first time, those theories were about to collide with reality. As the first high-resolution images began streaming back from Near Shoemaker's cameras, it became clear, quickly and unmistakably, that Eros was not what anyone had expected. The first close-up images of Eros arrived at the Johns Hopkins Applied Physics Laboratory in February of 2000, and they stopped conversations in their tracks. Not because they showed something familiar, because they showed something genuinely alien, and yet also, in a strange way, recognizable. Here was a world that looked like nothing on Earth, nothing on the Moon, nothing on Mars. And yet it was made of the same materials, the same minerals, the same elements, the same ancient, primordial stuff that had been drifting through the inner solar system for 4.5 billion years, unchanged, unaltered, waiting. Eros revealed itself as a battered, scarred, deeply textured body, roughly the shape of a bent shoe or a deformed kidney bean, depending on the angle and the lighting and the imagination of the person looking at it. Its surface was a complex tapestry of craters, ridges, grooves, slopes, flat terraces, and boulders. Thousands upon thousands of boulders. Some were the size of family homes. Some were the size of warehouses. Some were the size of office buildings, sitting on the surface like monuments left behind by some ancient catastrophe. One enormous boulder near the rim of a large impact crater, a crater the science team named Shoemaker, after the legendary planetary geologist Eugene Shoemaker, measured roughly 100 meters across. A boulder the size of a football field, perched on the surface of a world where gravity is barely strong enough to hold a sheet of paper in place. How did it get there? How had it not been knocked off by subsequent impacts? How was it sitting there, stable, unbothered, after billions of years? The science team named many features on Eros after famous lovers from literature and mythology. Psyche, Cupid, Don Quixote, Dulcinea, Casanova, Lolita, Romeo, Juliet, keeping with the romantic naming tradition that began with the asteroid's own name. It gave the maps a strange poetic quality. A crater called Himeros, a ridge called Rahe Dorsum, a saddle called Valentine, as if the landscape of this ancient, battered world was somehow tender beneath its scars. But it was not the boulders or the names that immediately puzzled the scientists. It was the craters, or more precisely, the craters that were not there. On the Moon, craters come in a predictable distribution of sizes. Small craters are extremely abundant. The surface is peppered with them, like rain on a pond. Larger craters are progressively rarer. The size distribution follows a well-understood power law, a mathematical relationship that reflects the population of impacting objects that have struck the Moon over billions of years. This same distribution has been observed on Mercury, on the moons of the outer planets, on nearly every airless body in the solar system. It is one of the most robust patterns in planetary science. But on Eros, the pattern was broken. The surface had plenty of large and medium-sized craters, but the small ones, craters below about 500 meters in diameter, were significantly underrepresented. They were not there in the numbers the models predicted. Something had erased them. Something had smoothed over the small impacts, while leaving the large ones more or less intact. And on a body with no atmosphere, no wind, no rain, no flowing water, no plate tectonics, on a body where nothing should be able to erase anything, that absence was deeply puzzling. This was the first major puzzle of the near Shoemaker mission. And the answer that scientists began to converge on was, in many ways, more unsettling than the mystery itself. The hypothesis was seismic shaking. Here is how it works. When a large object strikes an asteroid, a meteorite, a cometary fragment, a piece of debris from a collision elsewhere in the belt, the impact sends shockwaves rippling through the body. On a large, solid planet like Earth, these shockwaves propagate through dense rock and are quickly damped by the planet's enormous mass. They cause earthquakes, yes, but the energy dissipates rapidly. The planet absorbs the blow. Eros cannot absorb blows. It is too small. It is only 34 kilometers long, and more critically, it is not solid. Its interior, as the density measurements would later confirm, is riddled with fractures and voids. The rock is cracked, broken, shattered by billions of years of cumulative impacts. And when a shockwave enters a fractured medium, it does not propagate cleanly. It bounces. It reflects off internal surfaces. It scatters. It reverberates. The entire body rings like a cracked bell, vibrating at frequencies and amplitudes that depend on the size of the impact and the internal geometry of the fractures. And when it rings, the loose material on its surface, the regolith, the fine-grained layer of broken rock and dust that blankets every airless body in the solar system, shakes. It bounces, it flows, it settles. On Earth, we understand this process intuitively. If you take a box of mixed nuts and shake it, the smaller nuts sink to the bottom while the larger ones rise to the top. This is called granular convection, or informally, the Brazil nut effect. On Eros, seismic shaking produces a version of this process on a global scale. When the asteroid is jolted by an impact, the regolith vibrates. Fine particles migrate downhill into topographic lows. Loose material fills in small craters from below, gradually leveling them, erasing them. Over billions of years, this process, called seismic erasure, can selectively destroy small craters while leaving large ones relatively unaffected. The large craters are simply too deep to be filled in completely. The small ones are not. They vanish, one vibration at a time, their scars smoothed over by the asteroid's own internal tremors. The signature of seismic erasure is exactly what Near Shoemaker observed: the deficit of small craters, the presence of large craters that appeared oddly shallow, as if they had been partially filled, the redistribution of fine material into low-lying areas, all of it consistent with a world that shakes itself smooth, slowly, relentlessly over geological time. But here is what makes this truly unsettling. If Eros is so internally fractured that seismic waves can reshape its entire surface, then what is holding it together? What prevents it from simply falling apart, like a sandcastle hit by a wave? The answer is almost nothing. Eros has so little gravity that the concept of weight on its surface is almost meaningless. A person standing on the surface of Eros would experience a gravitational acceleration roughly 6/1000th that of Earth. If you weigh 70 kilograms on Earth, you would weigh about 40 grams on Eros, less than a AA battery. You could lift a boulder the size of a car with one hand. You could jump and reach a height of several kilometers before drifting slowly back down. Sprint along the surface, and you would achieve escape velocity, 10 meters per second, roughly 22 miles per hour, which means you would leave the asteroid entirely and never come back. The forces holding this world together are so faint they are barely distinguishable from nothing, and yet Eros endures. For 4.5 billion years, it has maintained its shape, its structural integrity, its identity as a single body. How? The density measurements provided the first real clue. By carefully tracking Near Shoemaker's orbit around Eros, measuring the spacecraft's position with radio signals to a precision of a few meters over a distance of hundreds of millions of kilometers, the science team calculated the asteroid's total mass, approximately 6.69 times 10 to the 15th kilograms, or about 6.7 quadrillion kilograms. Combined with a detailed three-dimensional shape model built from more than 160,000 images and 11 million laser altimetry measurements, this gave a bulk density of about 2.67 grams per cubic centimeter. That number is crucial. The minerals that make up Eros, the olivines, the pyroxenes, the feldspars, have densities of around 3.2 to 3.4 grams per cubic centimeter when measured in the laboratory. If Eros were a solid, unbroken chunk of these minerals, its density should have been higher than what was measured. The fact that the measured density was lower, significantly lower, meant that a substantial fraction of the asteroid's interior volume was not filled with rock. It was filled with nothing. Empty space, voids, fractures, gaps between broken fragments. The calculations suggested that roughly 20 to 30% of Eros's interior was void space. 1/5 to 1/3 of the asteroid was emptiness. It was not a monolith. It was a shattered body, cracked through and through, its fragments still interlocking but separated by internal voids, like a broken mosaic whose pieces have not yet scattered. Scientists use a specific term for this kind of body, a shattered aggregate. It is distinct from a rubble pile, though the difference is important and often misunderstood. A rubble pile, like the asteroid Itokawa, which Japan's Hayabusa mission would later visit, is a collection of loose fragments with no cohesive strength, held together purely by gravity. The pieces are separate. They are not connected. They simply lie on top of each other, kept in place by the feeble gravitational attraction between them. A shattered aggregate, by contrast, still has large-scale structural integrity. The fragments are cracked, but not separated. They interlock. They press against each other. They are held in place not just by gravity, but also by friction and by the mechanical resistance of their jagged, irregular surfaces pressing together. Think of a porcelain vase dropped from waist height onto a carpeted floor. It shatters, but if you are quick, you can catch it before the pieces separate. Every fragment is still touching its neighbors. The vase holds its shape. From the outside, it might even look intact, But inside, it is broken. That is Eros. Broken inside, intact outside, held together by the barest mechanical and gravitational forces imaginable. A 4.5 billion-year-old fragment of the early solar system, fractured to its core but stubbornly refusing to fall apart. And it gets worse. The grooves became the next obsession. Near Shoemaker's cameras revealed dozens of long, narrow troughs cutting across the surface of Eros, some stretching more than 20 kilometers in length and up to several hundred meters wide. They were linear, or nearly so. They ran in parallel sets in some areas and crossed each other at oblique angles in others. Some were shallow, others were deep. Some had raised rims, suggesting compression. Others looked like they had been carved or pulled apart, suggesting extension. These grooves looked disturbingly similar to features observed on Phobos, the larger of Mars's two tiny moons, which some scientists have argued was itself a captured asteroid. On Phobos, the grooves have been attributed to tidal stresses, the differential gravitational pull of Mars stretching and squeezing the moon as it orbits, or to the fracturing caused by the massive impact that created the giant crater Stickney. On Eros, no such external force was obvious. Eros does not orbit a planet. It orbits the Sun, far from any body massive enough to exert significant tidal forces. So what caused its grooves? The leading interpretation tied the grooves to the same process that explained the fractured interior. A catastrophic impact. One particularly prominent groove, called Rahe dorsum, ran for roughly 18 kilometers across one hemisphere of Eros, flanked by a raised ridge that gave it the appearance of a wrinkle in the asteroid's skin. The science team interpreted Rahe dorsum as a compressive feature, a fold in the surface created when a massive impact somewhere on the asteroid sent shockwaves through its interior, fracturing the body and causing the outer shell to buckle and deform. If that interpretation is correct, then Rahe dorsum is the visible scar of the blow that shattered Eros, the single, catastrophic event that cracked the asteroid from inside without quite tearing it apart. The impact that turned a once solid rock into a fractured shell. That impact likely occurred billions of years ago, in the chaotic early history of the solar system, when collisions between asteroids were far more frequent and far more violent than they are today. The early solar system was a shooting gallery. Bodies collided constantly, some merged, some shattered, some were ground to dust. The survivors, the ones that made it through that violent epoch relatively intact, are the asteroids we see today. Eros was one of those survivors, but it barely made it. The blow that fractured it came close to destroying it entirely. A slightly harder hit, a slightly different angle, and Eros would have broken into fragments that would have drifted apart and become separate asteroids. Instead, it held together, just barely, just enough. The story of what happened after that shattering blow is written in the asteroid's regolith, the layer of loose, broken rock and dust that covers its surface. And this is where the near Shoemaker mission delivered its strangest and most haunting discovery. The regolith on Eros was not uniform. In some areas, the surface was rough, chaotic, strewn with boulders and jagged rocks in every direction. These areas looked like the aftermath of an explosion, debris scattered across a landscape without order or pattern. But in other areas, particularly inside certain craters and in low-lying saddle regions, the surface was extraordinarily smooth, almost unnervingly so. These smooth areas were covered in a layer of fine-grained material that formed broad, flat, featureless deposits. The science team called them ponds. The ponds of Eros became one of the most famous and most perplexing discoveries of the entire mission. They were small, most no more than a few tens of meters across, but they were conspicuous against the otherwise rough and chaotic terrain. Their surfaces were flat, level to within a degree or two of horizontal, and they were always found in gravitational lows, the bottoms of craters, the insides of depressions, the concavities and saddles where loose material would naturally accumulate if it were somehow mobilized. They looked like puddles, frozen, dusty, silent puddles on a world where no liquid has ever existed, where no wind has ever blown, where no force, or so it seemed, should have been able to create such smooth, level deposits. How did they form? The question launched a vigorous scientific debate that continued for years after the mission ended and has never been fully resolved. One hypothesis invoked electrostatic levitation. The idea is that solar ultraviolet radiation and solar wind particles can electrically charge the fine dust on the surface of an airless body. On the sunlit side, the dust acquires a positive charge. On the shadow side, it acquires a negative charge. The resulting electric fields, though extremely weak, can be strong enough to levitate the finest particles, grains smaller than 100 microns, lifting them briefly off the surface and allowing them to drift horizontally before settling back down. If this process operates preferentially in topographic lows, where the electric field geometry concentrates the levitated particles, it could, over millions of years, build up the smooth, flat deposits observed in the ponds. Another hypothesis pointed to seismic shaking, the same process invoked to explain the deficit of small craters. Each time Eros is jolted by an impact, the vibrations cause the finest particles in the regolith to migrate downslope, flowing like a granular fluid into the topographic lows. Over billions of years, this slow, intermittent process could accumulate fine-grained material in exactly the locations where the ponds were observed. A third hypothesis invoked thermal cycling. As Eros rotates every 5 hours and 16 minutes, its surface alternates between sunlight and shadow. In sunlight, the surface heats up rapidly. Temperatures can reach roughly 100 degrees Celsius on the sunlit side. In shadow, they plunge to roughly negative 150 degrees Celsius. This extreme thermal cycling, repeated billions of times over the age of the asteroid, causes rocks to expand and contract, slowly breaking them apart through a process called thermal fatigue. The fragments become progressively finer with each cycle. Eventually, the finest particles are small enough to be mobilized by other forces: electrostatic levitation, seismic shaking, even the gentle pressure of sunlight itself, and they migrate into the topographic lows, forming ponds. No single explanation accounts for everything. The remarkably flat surfaces, the sharp boundaries between the ponds and the surrounding rough terrain, their consistent location in gravitational lows, their apparent age, which some researchers estimated at only a few 100 million years, based on the number of tiny craters on their surfaces, far younger than the asteroid itself. Each hypothesis explains some features but not others. The ponds of Eros remain, more than 2 decades after the mission ended, one of the most intriguing unsolved puzzles in asteroid science. And then there was the composition question, the one that had haunted planetary science for decades. Were S-type asteroids like Eros truly the parent bodies of ordinary chondrites? The spectral mismatch said no, or at least not obviously. Space weathering said the mismatch was cosmetic, but nobody had ever tested it directly. Nia Shoemaker's X-ray spectrometer and gamma-ray spectrometer could measure the elemental composition of the surface directly, detecting the characteristic X-ray and gamma-ray emissions produced when cosmic rays and solar X-rays struck the asteroid's surface atoms. These measurements bypassed the ambiguous spectral data entirely. They did not care what color the surface was. They measured what the surface was made of. And when those measurements came in, they told a story that was profoundly satisfying. The ratios of key elements, magnesium to silicon, iron to silicon, aluminum to silicon, calcium to silicon, were consistent with ordinary chondrite meteorites. Not identical, not a perfect match, but close. Close enough to strongly support the hypothesis that S-type asteroids and ordinary chondrites are indeed related. The spectral mismatch was a mask, created by space weathering, just as the hypothesis had predicted. Underneath that mask, Eros was made of the same primordial material that rains down on Earth as meteorites. The mystery that had nagged planetary science for 30 years was, if not definitively solved, then at least brought within sight of resolution. But here is the problem. One element was conspicuously, stubbornly, inexplicably depleted on the surface of Eros: sulfur. The sulfur abundance measured by the X-ray spectrometer was roughly half of what ordinary chondrites contain. This was not a trivial discrepancy. Sulfur is a volatile element, relatively easy to drive off by heating. Its depletion could mean that the surface of Eros had been thermally processed, heated enough to lose sulfur, perhaps by close approaches to the Sun during some earlier phase of its orbital history, or by the intense heat generated during the catastrophic impact that fractured its interior. Alternatively, it could mean that space weathering selectively removes sulfur from the surface, a process that had been theorized but never confirmed. Or it could mean something entirely different. Something about the relationship between asteroids and meteorites that is more nuanced, more complicated, more interesting than a simple parent-body connection. The sulfur mystery remains unsolved. It is one more thread in the ever-growing tapestry of questions that Eros left behind. And underlying all of these puzzles, the erased craters, the fractured interior, the mysterious ponds, the spectral mask, the missing sulfur, was the deepest, most fundamental question of all. The one that connected Eros not just to the history of the solar system, but to the future of the planet we live on. Where did Eros come from, and where is it going? Eros is a near-Earth asteroid. Its orbit crosses inside Mars and brings it within 22 million kilometers of Earth at closest approach. But near-Earth orbits are not stable. They are dynamically chaotic. Gravitational tugs from the planets, especially Jupiter and Mars, gradually alter an asteroid's orbit over millions of years, stretching it, tilting it, nudging it in unpredictable directions. Computer simulations suggest that the typical dynamical lifetime of a near-Earth asteroid is only about 10 million to 100 million years. After that, the asteroid either crashes into a planet, spirals into the Sun, or is ejected from the inner solar system entirely. But Eros is 4.5 billion years old. It was not born in a near-Earth orbit. It was born in the main asteroid belt, and it was delivered to its current orbit relatively recently, within the last few tens of millions of years, by gravitational resonances with Jupiter. And this means its time near Earth is limited. Its orbit will continue to evolve, it will drift, it will be nudged, and there is a small but non-zero probability, calculated by orbital dynamicists and published in peer-reviewed journals, that over the next million years, Eros's orbit could evolve into a collision course with Earth. If that happens, the consequences are almost too enormous to describe. Eros is roughly the same size as the impactor that created the Chicxulub crater 66 million years ago, the impact that killed the dinosaurs and 75% of all species on Earth. An Eros-sized impact would release energy equivalent to billions of nuclear weapons. It would vaporize thousands of cubic kilometers of rock. It would generate earthquakes, tsunamis, and firestorms across entire hemispheres. It would loft trillions of tons of debris into the upper atmosphere, blocking sunlight for months, possibly years, triggering a global winter that would collapse ecosystems worldwide. It would be the end of civilization, possibly the end of most complex life on the planet. But here is what makes this truly terrifying. Even if we detected such an impact decades in advance, deflecting Eros would be extraordinarily difficult. Because Eros is not solid, it is fractured, shattered, held together by friction and the barest gravitational whisper. Push on it the wrong way, hit it with a kinetic impactor, try to deflect it with a nuclear detonation, and instead of changing its orbit, you might break it apart. You would turn one 34-kilometer threat into thousands of smaller ones, a swarm of fragments, each one still potentially devastating, now spread across a wider and more unpredictable area. The very thing that makes Eros scientifically fascinating, its fractured, shattered, ancient structure, is exactly what makes it a nightmare for anyone trying to protect the Earth. And so, the mission that was designed to answer scientific questions also, inadvertently, raised one of the most urgent practical questions facing our species. How do you deflect an asteroid that might shatter if you push it? The gravity field data deepened the problem in ways that were not immediately obvious. By tracking the tiny wobbles in near Shoemaker's orbit, fluctuations caused by the uneven distribution of mass inside the asteroid, scientists could build a map of the internal density distribution. What they found was not a uniform body. Eros was denser in some regions than others. The mass concentrations, or maskons, were not distributed randomly. They seemed to follow patterns related to the large-scale shape of the asteroid, suggesting that Eros's interior, while fractured, still retained some memory of its original structure. The fractures had broken the body without completely scrambling it. The pieces were cracked but still roughly in their original positions, like a jigsaw puzzle that has been dropped but whose pieces have not been scattered. This is a remarkably precarious state for any object to be in for 4.5 billion years. It means Eros has not been hit by anything large enough to fully disrupt it since the original shattering event. Every subsequent impact, and there have been thousands, as the cratered surface testifies, has been small enough to chip and scar the surface without delivering enough energy to overcome the friction and mechanical interlock holding the broken interior, or together. Eros has been living on borrowed structural time for billions of years. It is, in a very real sense, a body on the edge, one large impact away from coming apart completely. And here is what connects all of these threads: the missing craters, the fractures, the grooves, the ponds, the composition, the sulfur mystery, the collision risk. They are all expressions of the same underlying truth. Eros is old, Eros is broken, Eros is barely holding together, and Eros is close. The asteroid orbits the Sun on a path that brings it regularly into Earth's vicinity. Not close enough to be an immediate threat, not in our lifetimes, not in our grandchildren's lifetimes, but close enough that on the timescales of geology and orbital mechanics, the encounter is inevitable. Someday, Eros will either hit something or be hit by something. It will either be deflected onto a new path, broken apart by a collision, swallowed by the Sun, or flung out of the inner solar system entirely. Its current state, tumbling silently through the void, fractured but intact, ancient but not eternal, is temporary. Everything about Eros is temporary, on a long enough timeline. The Near Shoemaker mission captured a snapshot of that temporary state, a single year of observation out of 4.5 billion years of history, a keyhole glimpse into the life of a body that has outlasted everything on our planet, every mountain, every species, every civilization, and yet is, in cosmic terms, living on the thinnest of margins. The scientists who analyzed the data understood this. Andrew Cheng, the mission's principal investigator, described Eros as a fragment of the early solar system, preserved in a state that no longer exists anywhere else. Other researchers were more blunt. Joseph Vervaeke, the imaging team leader from Cornell University, called the discovery of the ponds completely unexpected and noted that the processes shaping the surface of Eros were unlike anything predicted by any theoretical model. Mark Robinson, who worked on the high-resolution imaging data, described the experience of seeing the surface of Eros in close-up for the first time as like visiting another planet, except this one was smaller than most cities and had been dead for longer than Earth has been alive. Something is wrong with our assumptions about the solar system. We tend to think of it as a stable, orderly place. Planets in their orbits, moons circling their planets, the asteroid belt sitting quietly between Mars and Jupiter, a ring of debris that minds its own business. But the reality, as Eros reveals, is far messier. The solar system is full of broken things, things that should not still exist, things held together by forces so weak they should have failed long ago, things that wander close to our planet on paths that are not fixed, not predictable, not safe. Eros is one of those things, and the mission that studied it gave us, for the first time, a real understanding of what such things are, not as abstractions, not as dots on a telescopic photograph, but as physical worlds, with histories and structures and futures of their own. What Near Shoemaker revealed was not just the nature of a single asteroid, it was the nature of the leftover debris of creation, the raw, unfinished, dangerously mobile remnants of a process that built everything we know, and that never truly ended. To understand why the Near Shoemaker mission mattered as profoundly as it did, you need to see it not as an isolated event, but as a turning point in a much longer story, a story that stretches across decades, involves multiple space agencies, spans hundreds of millions of kilometers, and is still being written today. The exploration of asteroids is not a single narrative. It is a chain of missions, each one building on the last, each one answering old questions and raising new ones, each one pushing the boundary of what humanity can do in the hostile emptiness of space. The first link in that chain was forged not by a mission dedicated to asteroids, but by one that was heading somewhere else entirely. In October of 1991, the Galileo spacecraft, bound for Jupiter and its moons, passed through the main asteroid belt and flew within 1,600 kilometers of a small, irregularly shaped body called 951 Gaspra. The encounter was brief, lasting only a matter of hours. The images Galileo returned were low resolution, by later standards, but they were the first close-up pictures of an asteroid ever taken by a spacecraft, and they immediately overturned assumptions. Gaspra was not a featureless rock. It was angular, faceted. Its surface was peppered with small craters, but conspicuously lacking in large ones. It looked, more than anything, like a broken fragment, a shard chipped off a much larger body by some ancient collision, and that is precisely what planetary scientists believe it is. Gaspra belongs to the Flora family, a group of asteroids that share similar orbits and compositions, all of which are thought to be the remnants of a catastrophic disruption event. A collision between two larger asteroids that shattered at least one of them into hundreds of pieces. The Flora family is, in essence, the debris field of a collision that happened roughly 200 million years ago, around the time the first dinosaurs were walking on Earth. Looking at Gaspra was looking at a piece of wreckage from a cosmic car crash, still drifting through the scene of the accident hundreds of millions of years later. 2 years after the Gaspra encounter, in August of 1993, Galileo flew past another, larger asteroid, 243 Ida, and this encounter produced one of the most genuinely shocking discoveries in the history of planetary science. As the imaging team sifted through the photographs, examining the views of Ida's elongated, heavily cratered surface, one of them noticed something strange in the background of one image. A tiny dot, a second object, floating near Ida but clearly separate from it. That dot turned out to be a moon, a tiny, egg-shaped satellite, barely 1.4 kilometers across, orbiting Ida at a distance of about 100 kilometers. The team named it Dactyl, after the mythical beings who were said to live on Mount Ida in Greek mythology. It was the first confirmed natural satellite of an asteroid, the first proof that asteroids could have moons, and its discovery fundamentally changed the way scientists thought about the dynamics of the asteroid belt. If Ida, a modest main belt asteroid, could capture or create a moon, then the gravitational interactions between asteroids were far more complex, far more dynamic, and far more interesting than the static picture that had prevailed for decades. The asteroid belt was not a junkyard. It was a living, evolving system, governed by gravitational dynamics that scientists were only beginning to appreciate. But these flybys, as groundbreaking as they were, could only reveal so much. A spacecraft screaming past an asteroid at several kilometers per second gets only minutes of close observation, a handful of images, a few spectra, a single density measurement. If the geometry is favorable, it is like trying to understand a city by glimpsing it from the window of a speeding train. To truly understand an asteroid, its surface, its interior, its history, its composition, its structure, you need to slow down, you need to stop, you need to stay. That is what Near Shoemaker was designed to do. And by the time it arrived at Eros on Valentine's Day of 2000, the scientific community was holding its breath. No spacecraft had ever orbited an asteroid. No spacecraft had ever spent more than a few hours in an asteroid's vicinity. The entire enterprise was without precedent, and the asteroid itself, a 34-kilometer-long fractured body with the gravitational pull of a dandelion seed, presented navigational challenges that no mission had ever faced. Orbiting a body as small and irregularly shaped as Eros is nothing like orbiting a planet. Around a planet, gravity is strong, predictable, and nearly uniform. The spacecraft settles into a stable orbit and, barring occasional thruster firings to maintain altitude, essentially coasts. Around Eros, gravity is feeble, uneven, and deeply influenced by the asteroid's lumpy, asymmetric shape. The gravitational field is not smooth, it is bumpy, with mascons and voids and ridges that tug the spacecraft in different directions depending on where it is in its orbit. A stable circular orbit is, for practical purposes, impossible. The navigation team had to constantly adjust Near Shoemaker's trajectory, firing small thrusters to correct for the gravitational irregularities, essentially flying the spacecraft continuously rather than letting it coast. The orbital campaign unfolded in carefully planned stages. Near Shoemaker initially inserted into a distant orbit, about 320 kilometers from the center of Eros, where the gravitational perturbations were relatively gentle, and the navigation team could characterize the gravity field before venturing closer. Over the following months, the orbit was progressively lowered, 200 kilometers, then 100, then 50, then 35. At each stage, the science return increased dramatically. The camera could resolve finer details. The spectrometers could map smaller patches of surface. The laser altimeter could measure the topography with greater precision, and at each stage, the navigation became more challenging, the margin for error smaller, the consequences of a mistake more severe. At the closest orbital distances, just a few tens of kilometers above the surface, near Shoemaker's cameras were resolving features smaller than a single meter across. Individual rocks, pebbles, the faint texture of the regolith itself, granular and uneven, like the surface of a dirt road seen from very close range. The images from these low orbits were among the most detailed ever taken of any body in the solar system, revealing a landscape of startling complexity and beauty. Eros, up close, was not the featureless grey potato that early telescopic observations had suggested. It was a textured, layered, visually rich world, with colours that varied subtly from region to region. Slight differences in the reflectivity and redness of the surface that mapped onto geological features and hinted at compositional variations beneath the space-weathered veneer. The science return from the year-long orbital campaign was staggering in its volume and richness. The camera returned more than 160,000 images. The laser rangefinder fired more than 16 million pulses at the surface, building up a topographic model of Eros so detailed that it captured every major crater, every ridge, every groove, and every significant boulder on the asteroid's surface. The X-ray spectrometer mapped the elemental composition of the sunlit hemisphere, confirming that the surface abundances of major rock-forming elements matched ordinary chondrites with striking fidelity. The gravity field, measured by tracking the subtle changes in the spacecraft's velocity as it orbited, revealed the internal density distribution of Eros, showing that the mass was distributed relatively uniformly, consistent with a body that was fractured throughout, but not separated into distinct rubble fragments. Each instrument built a different layer of understanding, and together they created a portrait of Eros more complete than that of any asteroid before or since. But the most audacious, most improbable chapter of the near-Shoemaker mission was still to come. And it began with a simple question: what if we tried to land? The idea originated with Robert Farquhar, the mission director, who had been quiet contemplating the possibility since before the spacecraft even launched. Farquhar was a legend in the world of orbital mechanics, a man who had designed the trajectory for the International Sun-Earth Explorer 3 mission in the 1970s, which became the first spacecraft to visit a comet. He had a talent for seeing possibilities where others saw constraints, and he saw, in the final weeks of the near-Shoemaker mission, an opportunity that was too good to waste. The spacecraft was nearing the end of its operational life. Its instruments had collected a wealth of data. Its fuel was running low. The scientific mission was, by any measure, a complete success. The standard procedure would have been to simply turn off the instruments, shut down the transmitter, and let the spacecraft's orbit decay naturally until it crashed into the surface uncontrolled, months or years later. But Farquhar did not want to end with a whimper. He wanted to land. Not because near Shoemaker was designed to land. It absolutely was not. It had no landing legs, no airbags, no shock absorbers, no retro-rockets calibrated for a gentle touchdown. Its solar panels were fragile. Its high-gain antenna was fixed and could not be repointed after landing. There was no guarantee at all, that the spacecraft would survive contact with the surface. But Farquhar argued that the potential scientific return justified the risk. The gamma-ray spectrometer, which had struggled to get clean measurements from orbit because of interference from the spacecraft's own radioactive materials, would work far better if it was sitting directly on the surface, with the asteroid's rock pressed right up against its detector, and the close-up images taken during the descent would provide views of the surface at a resolution never before achieved, not just on Eros, but on any asteroid. The mathematics of the descent were calculated with a precision bordering on the obsessive. The plan called for a series of 5 deorbit burns, beginning on January 28, 2001. Each burn would lower the orbit slightly, bringing the spacecraft closer to the surface in a controlled, deliberate spiral. The target landing area was a saddle-shaped region called Eros, one of the broadest and flattest terrains on the asteroid's surface, chosen because it offered the lowest topographic relief and therefore the least chance of the spacecraft striking a boulder or tumbling into a crater on contact. The final descent began on February 12, 2001. Over the course of approximately 4.5 hours, near Shoemaker spiraled down from an altitude of about 16 kilometers, its thrusters firing in carefully timed bursts to control the rate of descent. During the approach, the spacecraft's camera snapped 70 images, each one more detailed than the last, each one showing the surface of Eros at a resolution that had never been achieved before. The final images, taken from an altitude of just 120 meters above the surface, showed individual pebbles, stones the size of fists, and the fine granular texture of the regolith at a scale of centimeters. These were not just photographs. They were windows into a world no human eye had ever seen. At approximately 3 o'clock in the afternoon Eastern Standard Time, the Doppler shift in the spacecraft's radio signal, the change in frequency caused by its motion toward or away from Earth, went to zero. The spacecraft was no longer moving, it was on the surface. It had touched down at a speed of approximately 1.5 to 1.8 meters per second, about the speed of someone walking slowly, setting their foot down with care. The spacecraft came to rest on a relatively flat patch of regolith, tilted slightly, but otherwise intact. Its solar panels were still generating power, its transmitter was still broadcasting, its instruments were still functioning. The room at the Applied Physics Laboratory erupted in cheers. Engineers and scientists who had spent years building and guiding this machine across billions of kilometers of empty space were on their feet, applauding, embracing, some of them weeping with relief and joy. A machine that was never designed to land had just executed the first ever controlled descent to the surface of an asteroid. It was an act of engineering elegance born from scientific ambition and a stubborn refusal to let a perfectly good spacecraft go to waste. For 16 days, Near Shoemaker operated from the surface of Eros. Its gamma-ray spectrometer, freed from the noise of the spacecraft's own radioactivity by the proximity of the surface, collected the most precise elemental composition data of the entire mission. The readings confirmed and refined the orbital measurements, the chondritic composition, the sulfur depletion, the abundances of iron, silicon, oxygen, magnesium. These 16 days of surface operations, unplanned and improvised, turned out to be among the most scientifically valuable of the entire mission. Then, on February 28, 2001, the final command was the transmitter was turned off. Near Shoemaker fell silent. It remains there today, sitting on the surface of Eros, a tiny metallic monument to human curiosity in a place no human eye will likely see for centuries. But the story of asteroid exploration did not end with Near Shoemaker. It accelerated. The success of the mission, its scientific return, its engineering achievements, its demonstration that small, focused, cost-effective missions could produce world-class results, inspired a new generation of asteroid missions, each one more ambitious than the last. In May of 2003, the Japan Aerospace Exploration Agency launched a spacecraft called Hayabusa, the Japanese word for peregrine falcon, toward a tiny near-Earth asteroid designated 25,143 Itokawa. The mission's goal was audacious beyond anything Near Shoemaker had attempted. Not just visit the asteroid, not just orbit it, not just land on it, but collect a sample of its surface material and bring it back to Earth. A round trip, an actual physical piece of another world, delivered to laboratories on our planet, where it could be studied with instruments far more powerful and precise than anything that could be carried on a spacecraft. Itokawa was a tiny body, just 535 meters long, roughly the size of 5 city blocks laid end to end. It was smaller than most college campuses. If you could somehow transport it to Earth and set it down in a major city, it would fit comfortably within a few neighborhoods. Compared to Eros, which stretches 34 kilometers, Itokawa was minuscule, and when Hayabusa arrived in September of 2005, after a journey of more than 2 years, The images it returned were shocking in their strangeness. Itokawa looked nothing like Eros. Where Eros was cratered and grooved and scarred by billions of years of impacts, Itokawa had virtually no craters at all. Its surface was divided into two starkly different terrains. Rough highlands, covered in boulders that ranged from pebble-sized to house-sized, packed so densely that there was almost no flat ground between them, and smooth lowlands, broad, gently curving depressions filled with fine gravel and small stones, looking for all the world like rocky beaches. The largest of these smooth regions, called the Muses Sea, covered a significant fraction of the asteroid's surface and had a startlingly uniform, almost manicured appearance. It looked like someone had raked it. But the most striking thing about Itokawa was its shape. It was clearly not a single, coherent body. It was two objects fused together, a contact binary, formed when two separate rubble piles drifted together at very low speed and gently merged, their touching surfaces becoming the narrow neck connecting the two lobes. The overall impression was of a lumpy, misshapen peanut, or, as some Japanese scientists memorably described it, a sea otter floating on its back. The density measurements confirmed what the shape suggested. Itokawa's bulk density was only about 1.95 grams per cubic centimeter, far less than the density of its constituent minerals. The implied porosity was roughly 40%. 40% of Itokawa was empty space. It was not a fractured but intact body like Eros. It was a genuine rubble pile, a loose collection of fragments with no cohesive strength, held together solely by gravity. Imagine a bag of sand and gravel floating in space, shaped by its own rotation and the gentle pull of its own mass. That is Itokawa, a world without a skeleton. The Hayabusa mission itself became a legend of perseverance in the face of almost unrelenting disaster. A solar flare early in the mission damaged the spacecraft's solar panels, reducing power. One of its 4 ion engines failed. Its reaction wheels, the spinning wheels used to control the spacecraft's orientation, broke down one by one. The sample collection mechanism malfunctioned during the first touchdown attempt. The spacecraft actually bounced off the surface of Itokawa, spending about 30 minutes on the asteroid without the mission team even realizing it had touched down. A fuel leak disabled the chemical thruster system, sending the spacecraft tumbling out of control. Communication was lost for weeks. At one point, the mission team at the Japanese Space Agency genuinely believed Hayabusa was dead, a silent, tumbling wreck drifting through interplanetary space. And yet, against odds that would have been laughable in fiction, Hayabusa survived. It limped home on its remaining ion engines, navigating by improvised methods that the engineering team invented in real time. It arrived back at Earth on June 13, 2010, 7 years after launch, 3 years behind schedule, and released its sample return capsule into the atmosphere over the Australian outback. The main spacecraft, its mission finally complete, re-entered the atmosphere and burned up in a streak of light that was visible from the ground. Observers described it as beautiful, a falling star that had once touched another world. The capsule was recovered. Inside, scientists found approximately 1,500 tiny grains of asteroidal material, 1,500 microscopic particles, each one smaller than a grain of sand, each one a messenger from a world 535 meters across, floating in the void between Mars and Earth. The total mass of the sample was measured in micrograms, barely enough to see with the naked eye, let alone hold in your hand. But those 1,500 grains changed everything. Under electron microscopes and mass spectrometers, they revealed their secrets. Their mineral composition matched ordinary chondrites almost perfectly. Their isotopic ratios were consistent with the inner solar system origin that had been hypothesized for S-type asteroids. And on their surfaces, the scientists found the smoking gun of space weathering, a nanometer-thin rind of altered material, rich in nanophase iron particles, coating each grain like a layer of tarnish on old silver. This was the mask. This was the cosmetic layer that had made S-type asteroid surfaces look different from the chondrite meteorites they were actually made of. 30 years of debate, resolved by 1,500 microscopic grains from a tiny asteroid that almost nobody outside of planetary science had ever heard of. The near Shoemaker data from Eros had pointed strongly toward this conclusion. The Hayabusa samples from Itokawa confirmed it definitively. The mystery was solved. But a solved mystery is also the birth of new questions. If S-type asteroids and ordinary chondrites were now understood, what about the other types? What about the dark, carbon-rich C-type asteroids that dominate the outer main belt? What about the carbonaceous chondrites? Primitive meteorites, loaded with water, organic molecules, and pre-biological chemistry, that are thought to come from these dark asteroids. What secrets did they hold about the origin of water on Earth, the delivery of organic molecules, and the chemical preconditions for life? To answer those questions, 2 new missions were launched within a few years of each other, one by Japan, one by the United States. And they would take the story begun at Eros to worlds even more ancient, even more primitive, and even more revelatory than anything that had come before. Hayabusa 2 launched in December of 2014, targeting an asteroid called 162,173 Ryugu. Ryugu was a C-type, a carbonaceous asteroid roughly 900 meters in diameter, shaped like a spinning top or a diamond, a form that scientists call a top shape, created by the centrifugal forces of rapid rotation pushing material toward the equator over millions of years. When Hayabusa 2 arrived in June of 2018, the images were stunning. Ryugu was dark, nearly as black as charcoal, and covered in boulders so densely packed that finding a safe landing site was a nightmare for the mission planners. There were almost no flat areas larger than a few meters across. The entire surface was a chaos of angular rocks, like a construction site after a demolition. The density was even more extreme than Itokawa. At roughly 1.19 grams per cubic centimeter, Ryugu was more empty space than solid matter, a porosity of more than 50%. It was so loosely packed that if you could somehow squeeze it, water would be denser. A rubble pile of extraordinary fragility, held together by gravity so weak that the escape velocity at its surface was only about 37 centimeters per second, slower than a crawling baby. But Hayabusa 2 did something extraordinary. It deployed a small copper projectile, essentially a bullet, that was fired into the surface of Ryugu at 2 kilometers per second, creating an artificial impact crater roughly 14 meters across. This was deliberate. By excavating subsurface material that had been shielded from space weathering and cosmic radiation for billions of years, the mission could sample pristine, unaltered asteroidal material. The spacecraft then descended into the artificial crater and collected a sample of the freshly exposed material. In December of 2020, the sample capsule returned to Earth, landing in the Australian outback just as Hayabusa's had done 10 years earlier. Inside was 5.4 grams of dark, crumbly asteroidal material, thousands of times more than Hayabusa had managed. And the analysis of that material produced results that sent shockwaves through the scientific community. The Ryugu samples contained amino acids, the building blocks of proteins, the molecular foundations of life. They contained nucleobases, the components of DNA and RNA. They contained water-bearing minerals, clays and hydrated silicates formed in the presence of liquid water, proving that Ryugu's parent body once had water flowing through it, billions of years ago, long before the asteroid was broken off and set adrift. The samples were, in a very real sense, a recipe for life, or at least the raw ingredients of a recipe, preserved in stone, sealed in darkness, drifting through space for 4.5 billion years, waiting for someone to come and read them. NASA's companion mission was OSIRIS-REx. Origins, spectral interpretation, resource identification, and security regolith explorer, launched in September of 2016 toward another carbonaceous asteroid, 101,955 Bennu. Bennu was smaller than Ryugu, just under 500 meters across, roughly the height of the Empire State Building. But it carried a significance that went beyond science. Orbital calculations showed that Bennu has a small but non-zero probability of impacting Earth in the late 2200s. It is officially classified as one of the most potentially hazardous asteroids in the solar system. Studying Bennu was not just scientific curiosity. It was planetary defense reconnaissance. When OSIRIS-REx arrived at Bennu, In December of 2018, it found a surface so densely packed with boulders that the original sample collection plan, designed for a relatively smooth terrain, had to be completely scrapped and redesigned from scratch. Every potential landing site was surrounded by rocks the size of buildings. The spacecraft had to navigate into a gap between boulders with a clearance of just a few meters, threading a needle at a distance of hundreds of millions of kilometers from Earth, with a time delay of more than 18 minutes between sending a command and receiving confirmation that it had been executed. The engineering challenge was almost absurd in its difficulty. On October 20th, 2020, OSIRIS-REx descended to the surface. It extended its robotic sampling arm, a device called TAGSAM, the touch-and-go sample acquisition mechanism, and made contact with the surface for approximately 6 seconds. During those 6 seconds, it fired a burst of nitrogen gas into the surface, stirring up a cloud of loose material, and captured a portion of that material in a collection canister. The amount collected exceeded all expectations, more than 250 grams of dark, carbon-rich asteroidal material, the largest sample of extraterrestrial material returned to Earth since the Apollo missions brought back lunar rocks in the early 1970s. The sample capsule was delivered to Earth on September 24, 2023, landing in the Utah desert under parachutes. Preliminary analysis revealed that Bennu's material contains water locked in hydrated minerals, abundant carbon in organic molecules, sulfur, phosphorus, and all the other elements essential for the chemistry of life. The minerals include serpentine and magnetite, clays and iron oxides that form only in the presence of liquid water under specific temperature and chemical conditions. These findings tell us that Bennu's parent body, whatever larger asteroid Bennu was once part of, had liquid water circulating through its interior in the early solar system. It had an active hydrothermal system, billions of years before any ocean existed on Earth. Each of these missions, Galileo's pioneering flybies, near Shoemaker's historic orbit and landing, Hayabusa's desperate and triumphant sample return, Hayabusa 2's bold excavation, OSIRIS-REx's needle-threading collection, tells a chapter of the same story. And Eros is the turning point. Before near Shoemaker, asteroids were abstractions, points of light in a telescope, entries in a catalogue, theoretical constructs in a computer model. After near Shoemaker, they were places, real worlds, with textures and landscapes and histories of their own. The mission did not just study one asteroid. It opened a door through which every subsequent mission walked. And what those missions have revealed, collectively, is something profound. Asteroids are not just rocks. They are the frozen memories of a time before planets existed. They carry water, organic molecules, amino acids, the fundamental ingredients of biology. They preserve a record of the solar system's infancy that no planet can match, because planets are too dynamic, too hot, too geologically active to preserve their earliest materials. Asteroids are the only time capsules we have, and the more closely we study them, the more clearly we see that the story of life on Earth, our story, is inseparable from the story of these ancient, drifting, battered, fragile worlds. Let that sink in. A spacecraft built by human beings, assembled from aluminum, silicon, copper, gold and glass, all of which were originally forged in the cores of stars that died before our sun was born, travelled 3 billion kilometers through the vacuum of space and gently touched down on a rock that has been drifting in silence since before the Earth existed. A rock so old that when it formed, our sun was still a collapsing cloud of gas and dust. A rock so ancient that every mountain range, every ocean, every living thing that has ever existed on our planet came into being long after Eros was already billions of years old. We reached out across the void and touched the past. That statement is not metaphor. It is not poetry. It is physics. The materials on the surface of Eros are among the oldest solid substances in the solar system. The ordinary chondrite composition measured by near Shoemaker's instruments dates the asteroid's constituent materials to approximately 4.56 billion years ago, within the first 10 million years of the solar system's existence, before the Earth had finished accreting, before the Moon existed, before the oceans filled, before the atmosphere thickened, before the first self-replicating molecule, before everything. When you hold an ordinary chondrite meteorite in your hand, a dark, dense, slightly metallic-feeling stone that was blasted off a body like Eros by some ancient collision and delivered to Earth over millions of years of orbital wandering, you are holding something older than any rock you could find on the ground beneath your feet. The oldest known rocks on Earth are about 4 billion years old, and they are vanishingly rare. Tiny crystals of zircon found embedded in younger sandstones in Western Australia, survivors of a geological recycling program that has been running for 4.5 billion years. The Earth destroys its own history. Plate tectonics subducts oceanic crust into the mantle. Erosion wears down mountains. Volcanism buries landscapes under lava. The Earth is a geological washing machine, constantly scrubbing away the evidence of its own past. But asteroids do not wash. They do not erase. They are too small for plate tectonics, too airless for erosion, too cold for volcanism, at least in the present era. They preserve their original state with a fidelity that no planet can match. They are the solar system's deep archive, and Eros is one of the oldest, most complete, most accessible entries in that archive. Here is the deeper truth, the one that only becomes visible when you step back from the individual discoveries, the individual missions, the individual data points, and look at the full picture of what asteroid science has revealed over the past 3 decades. We are made of the same stuff. This is not a poetic metaphor. It is a literal, measurable, chemically verifiable fact. The silicon in the screen you are watching this on was formed in the core of a star that lived and died billions of years before the sun existed. The iron in your blood was fused in the final moments of a massive star's life, in the runaway nuclear reactions of a supernova explosion. The calcium in your bones was synthesized in the helium-burning shells of red giant stars, then scattered into the interstellar medium when those stars shed their outer layers. The oxygen you are breathing right now, every molecule of it, was forged in stellar furnaces and ejected into space in stellar winds and supernova remnants. When the sun formed from a collapsing cloud of this enriched, pre-processed interstellar material roughly 4.6 billion years ago, the leftover debris, the dust, the grains, the tiny fragments of condensed minerals formed a disk around the young star. Within that disk, the grains collided, stuck together, and slowly built up into larger bodies. Some of those bodies became planets, some became moons, some became comets, and billions of them stalled out, never growing large enough to undergo the heating and differentiation that would transform their interiors into the layered structures of planets. Those stunted bodies are the asteroids, and they carry, locked in their minerals, the original recipe from which everything else was made. The chondrules embedded in ordinary chondrites, the tiny millimeter-sized spherical droplets of silicate that give chondrites their name, are among the most primitive solid objects in existence. They formed in the solar nebula itself, heated by brief, intense events, possibly shock waves, possibly lightning, possibly energetic outbursts from the young sun, and then cooled and solidified within hours or days. They are, in the most literal sense, the first solids, the first concrete things, the first objects that could be held, weighed, measured, and studied, the first grains of matter in a universe that had, until that moment, known only gas and light and gravity. Every atom in your body was once part of something like that, not necessarily on Eros itself, but in the same cloud, the same disk, the same epoch of creation, the same batch of cosmic raw material, processed through the same stellar fires, condensed in the same nebula cooling, assembled by the same gravitational forces. The difference between you and the asteroid is not a difference of substance, it is a difference of history. Eros stayed simple. You became complex. Eros remained cold and still and dark. You were heated, compressed, melted, differentiated, cooled, weathered, subducted, erupted, eroded, dissolved, precipitated, photosynthesized, metabolized, evolved, specialized, complexified, and eventually made conscious. But the starting materials are the same. You and Eros are siblings, separated at birth by 4.5 billion years of divergent history. Let that sink in. There is another dimension to this truth, and it is the one that is hardest to sit with. It concerns time. And what time means for a body like Eros compared to what it means for a world like ours. Eros has survived for 4.5 billion years. It has endured countless impacts. Its interior has been shattered but never fully disrupted. It has weathered the slow bombardment of the solar wind, the relentless rain of cosmic rays, the thermal stress of 5-hour days and 5-hour nights repeated billions of times. It has been nudged out of the main belt by Jupiter's gravitational resonances and delivered to a chaotic near-Earth orbit where it could be flung into the Sun or onto a collision course with a planet at any time. And through all of this, it has persisted. It is still here, still tumbling, still circling the Sun, still carrying its ancient cargo of primordial minerals unchanged through the darkness. In the same 4.5 billion years, Earth has been remade almost beyond recognition over and over. Its surface has been completely resurfaced by plate tectonics dozens of times. Its atmosphere has been transformed from a reducing mix rich in carbon dioxide, methane, and ammonia to the oxygen-nitrogen blend we breathe today. Its oceans have formed, partially frozen over at least twice in global glaciation events called Snowball Earth, and had their chemistry altered by the metabolic activities of billions of generations of microorganisms. Life has appeared, diversified, been nearly wiped out at least 5 times, and recovered each time in a different form. Continents have drifted across the globe, collided to form supercontinents, then split apart again. The Earth is a world in constant upheaval, a planet that devours its own past and rebuilds itself from the wreckage. Eros is the opposite, a monument to stillness, a record of what things were like at the very beginning, preserved in stone and dust and silence. Its craters are its memory, its grooves are its scars. Its composition is its autobiography, written in the language of elements and isotopes and mineral phases, readable by anyone with the right instruments, the patience to travel 3 billion kilometers, and the curiosity to look, the physicist Carl Sagan said, in a different context, that we are a way for the cosmos to know itself. If that is true, then the near Shoemaker mission was the cosmos inspecting its own baby pictures, a product of stellar evolution, human beings made of stardust, standing on a planet made of stardust, sent a machine made of refined stardust across the void to study a piece of raw, unprocessed stardust that has been sitting in cold storage since before any of them existed. But there is a tension in this story, and it is the tension that drives everything, because asteroids are not just archives, they are also weapons. The same bodies that carry the recipe for life are the same bodies that can end it. 66 million years ago, an asteroid roughly 10 to 15 kilometers across struck the Earth near what is now the Yucatan Peninsula of Mexico. The impact released energy equivalent to roughly 10 billion Hiroshima bombs. It punched a crater 180 kilometers wide and more than 20 kilometers deep. It generated tsunamis that swept entire ocean basins. It hurled trillions of tons of pulverized rock and sulfur-rich vapor into the upper atmosphere, blocking sunlight for months, possibly years, dropping global temperatures by more than 10 degrees Celsius, acidifying rainfall, and triggering a cascading collapse of ecosystems from the base of the food chain upward. The non-avian dinosaurs, which had dominated the planet for more than 160 million years, were wiped out. Along with them went roughly 75% of all species. It was the most catastrophic single event in the history of complex life on Earth. That impact was not extraordinary. It was not a freak accident. It was the natural, inevitable consequence of living in a solar system still populated by the leftover debris of planetary formation. Asteroids have been striking Earth for as long as Earth has existed. The early bombardment was orders of magnitude more intense than today. The late heavy bombardment, roughly 3.9 billion years ago, may have delivered enough energy to boil the oceans. Even today, small asteroids strike the Earth regularly. The Chelyabinsk event of 2013, when a roughly 20-meter asteroid exploded in the atmosphere over Russia, injured more than 1,500 people and damaged thousands of buildings. It was a reminder, dramatic, unexpected, and deeply uncomfortable, that the cosmos is not done throwing things at us, and Eros is one of the things the cosmos could throw. It is approximately the same size as the Chicxulub impactor. An Eros-sized impact on Earth would be an extinction-level event. It would end civilization. It might end humanity. The probability is low for any given century. but on geological timescales, it approaches certainty. The only question is when. This is not science fiction. Something is wrong with our assumptions about safety in the solar system. We treat the ground beneath our feet as stable. We treat the sky above our heads as benign. We build cities and civilizations and cultures on the assumption that the Earth is safe, that the major threats to our survival come from ourselves, from our wars and our pollution and our carelessness. And those threats are real. But they are not the only ones. The universe has its own arsenal, and it does not negotiate. The Near Shoemaker mission gave us our first real understanding of what that arsenal looks like up close. A fractured, shattered, ancient body carrying enough mass and velocity to destroy a world. And not just any fracked body, but one whose internal structure makes it extraordinarily difficult to deflect. Push on Eros, and you might shatter it. Try to change its course, and you might create a swarm. The same fragility that makes asteroids scientifically precious makes them operationally nightmarish for anyone charged with protecting the Earth. NASA's DART mission, which successfully changed the orbit of the tiny asteroid Dimorphos in September of 2022, demonstrated that kinetic impact deflection works, at least for small, rubble pile bodies. But Dimorphos was 160 meters across. Eros is 34 kilometers across, 200 times larger. The physics does not scale linearly. The strategies that work for small bodies may not work for large ones. And for fractured bodies like Eros, shattered aggregates, broken inside but intact outside, the problem is qualitatively different. We simply do not yet know how to reliably deflect a body like that, and we may not know until the day we need to. That truth, the gap between our understanding and our capability, between our curiosity and our preparedness, is perhaps the most important legacy of the Near Shoemaker mission. Not the scientific data, not the engineering achievements, not the photographs, but the realization that the universe is more dangerous than we pretend, and more beautiful than we imagine, and more indifferent than we can comfortably accept. Consider for a moment what the ponds of Eros tell us about time. Those smooth, flat deposits of fine dust, sitting quietly in the bottoms of craters and depressions, were not placed there by any sudden event. They accumulated, grain by grain, particle by particle, over hundreds of millions of years. Each vibration of the asteroid, caused by an impact somewhere on its surface, shook loose a thin layer of fine material and redistributed it, a fraction of a millimeter at a time. The ponds grew the way stalactites grow in a cave, invisibly, imperceptibly on timescales so vast that no observer could ever witness the process. You would have to watch for 10 million years to see a measurable change, 100 million years to see the ponds take shape, 1 billion years to see them mature. We are not built for those timescales. The human mind evolved to track threats on the scale of seconds, to plan on the scale of seasons, to remember on the scale of decades. We can imagine 1 million years in the abstract, but we cannot feel it. We cannot experience it. We cannot truly understand what it means for a process to operate continuously for longer than our species has existed, longer than most species have existed, longer than complex life itself has existed on this planet. The ponds of Eros are a meditation on patience that the human mind is physiologically incapable of fully appreciating. They are, in that sense, a kind of cosmic art, beautiful, tranquil, and completely beyond our emotional reach. And yet we try. We send machines to photograph them. We build computer models to simulate them. We write papers about them, debate them at conferences, argue about the relative contributions of electrostatic levitation and seismic shaking and thermal fatigue. We try to understand a process that operates on a timescale 4 orders of magnitude longer than human civilization. There is something deeply moving about that effort, something that says more about our species than any photograph ever could. The same is true of the mission as a whole. Near Shoemaker was not just a scientific experiment. It was an act of curiosity so profound that it transcended its own context. The people who designed the mission, who built the spacecraft, who navigated it across 3 billion kilometers of void, who talked it down to the surface of a tumbling rock in the dark, those people were not motivated by a desire for profit, or power, or fame. They were motivated by the same impulse that drove the first humans to look up at the sky and wonder what the lights were. The impulse to know, the impulse to understand, The impulse that takes a conscious mind and points it at the universe and says, I want to see what is out there. That impulse is, as far as we know, unique to us. No other species on Earth builds telescopes. No other species launches rockets. No other species sends robots to land on asteroids and measure the elemental composition of their surfaces with X-ray spectrometers. We are the universe's only known attempt at self-comprehension. And near Shoemaker, sitting on the surface of Eros in permanent silence, is a physical embodiment of that attempt. There is a thought experiment that sometimes comes up in conversations about asteroid science, and it goes like this. Imagine that Eros could somehow know it was being studied. Imagine that this ancient, battered, fractured body, older than the Earth, older than the Moon, older than the oceans, could somehow perceive the tiny machine that touched its surface on that February afternoon in 2001. What would it make of us? What would a 4.5 billion-year-old rock think of a species that has existed for 300,000 years, that has been building machines for maybe 10,000, that has been leaving its planet for barely 60? The answer, of course, is that Eros would think nothing. It is a rock. It cannot think. It cannot know. But we can. And that asymmetry, the fact that we are aware of Eros, but Eros is not and can never be aware of us, is itself a kind of revelation. It tells us something about the nature of consciousness and its place in the universe. We are temporary. We are fragile. We are recent arrivals on a stage that has been set for billions of years. But we are the only ones who know the stage is there. We are the only ones who can read the script. And in that reading, in the act of understanding what Eros is and where it came from and what it tells us about the cosmos, there is something that transcends the mere accumulation of data. There is meaning. Not meaning that the universe provides, meaning that we create by paying attention, by caring, by refusing to look away. The Near Shoemaker mission ended more than 25 years ago. The spacecraft still sits on the surface of Eros, inert, silent, slowly being buried by the same fine dust that fills the ponds around it. Grain by grain, particle by particle, the regolith is creeping over it. In a few million years, it may be completely covered. A metal fossil embedded in the surface of an alien world, indistinguishable from the boulders and rocks around it, unless someone knows exactly where to look. But the knowledge it returned is not inert. It is alive. It lives in the papers and databases and textbooks that preserve the mission's results. It lives in the missions that followed: Hayabusa, Hayabusa 2, OSIRIS-REx, DART, each one building on what Near Shoemaker revealed. It lives in the understanding that asteroids are not just rocks, not just threats, not just abstractions, but worlds. Real, tangible, ancient worlds with stories of their own. Stories that intertwine with ours in ways that are both humbling and terrifying. And it lives in the questions that remain unanswered. What formed the ponds? Why is sulfur depleted? How do you deflect a body that is fractured inside? Will Eros ever hit the Earth? Can we stop it if it does? These questions are the mission's living legacy. Not closed files, but open doors, invitations to the next generation of scientists and engineers and dreamers to continue the work that began when a small spacecraft named after a legendary geologist touched down on a rock named after a god of love. What does it mean to have touched an asteroid? It is easy to answer that question with data. We measured the mass, we mapped the shape, we identified the minerals. We confirmed the link between S-type asteroids and ordinary chondrite meteorites. We discovered ponds and grooves and boulders, and a fractured interior held together by the thinnest gravitational thread. We produced more than 160,000 images and 11 million topographic measurements and enough spectral data to fill libraries. These are the facts of the mission, and they are significant, and they changed our understanding of the solar system in ways that will reverberate through planetary science for decades. But the facts are not the whole story. The whole story is about what it means for a species that has existed for an eye blink of cosmic time to reach out across hundreds of millions of kilometers and make physical contact with an object that has been drifting in silence since before the Earth was born. Think about the chain of events that had to unfold for this to happen. First, a cloud of interstellar gas and dust had to collapse under its own gravity, roughly 4.6 billion years ago. forming a protostar surrounded by a swirling disk of debris. Within that disk, grains of mineral had to collide and stick together, building up, over millions of years, into the rocky cores of planets and the smaller fragments we call asteroids. One of those fragments, Eros, had to survive the chaotic early solar system without being swallowed by a growing planet, shattered beyond recovery, or ejected from the inner system. It had to endure billions of years of bombardment, gradually accumulating craters and boulders, and a thin blanket of regolith while its interior fractured but held. Meanwhile, on one of the planets that did form, a medium-sized rocky world orbiting at just the right distance from the Sun for liquid water to exist on its surface. An extraordinary sequence of events had to unfold. Simple chemistry had to become complex chemistry. Complex chemistry had to become self-replicating chemistry. Single-celled life had to appear, diversify, and eventually, after billions of years of evolution, give rise to multicellular organisms, then to animals, then to primates, then to a species capable of abstract thought, language, mathematics, and engineering. That species had to develop metallurgy, optics, rocketry, computing, and orbital mechanics, all within a span of a few thousand years, less than a millionth of the asteroid's lifetime. And then that species had to decide, collectively, to build a machine and send it to that particular asteroid for the purpose of understanding it. The improbability of this sequence is staggering. Change any single variable. The mass of the Sun, the timing of a collision, the chemistry of the primordial ocean, the mutation of a single gene, and the outcome might have been entirely different. Near Shoemaker might never have flown. Eros might never have been studied. The questions it raised might never have been asked. And yet here we are, with data and images and measurements from the surface of an asteroid that formed before any life on Earth existed. Here we are, with a spacecraft sitting silently on the surface of that asteroid, a metallic bookmark in the pages of the solar system's oldest chapter. The sheer improbability of the chain of events that led to this moment is, in itself, a kind of miracle. Not a supernatural one, but a natural one. The kind of miracle that emerges when the laws of physics are given enough time and enough raw material to play with. The Near Shoemaker mission also crystallized a truth about human civilization that is easy to forget in the noise of daily life. We are a spacefaring species, not in the science fiction sense of colonizing galaxies or traveling at the speed of light, but in the literal, measurable, verifiable sense of having built machines that travel between worlds. We have sent robots to Mars, to Jupiter, to Saturn, to Pluto, to comets and asteroids, and the heliopause at the edge of the solar system. We have walked on the moon. We have sampled the surface of asteroids and brought pieces of them back to Earth. These are not speculations or ambitions. They are accomplished facts, and they mark our species as something genuinely unprecedented in the known history of the universe, a form of organized matter that has developed the ability to project itself across astronomical distances. Eros sits at a pivotal point in this story. It was the first asteroid we orbited, the first we landed on, the first we studied not as a distant point of light, but as a physical place, a landscape, a world with its own geography and its own history. Before Near Shoemaker, the word asteroid evoked something abstract, a shape on a chart, a data point in a catalogue, a potential threat on a probability table. After Near Shoemaker, the word evoked something concrete. Craters named after lovers, boulders the size of buildings, strange smooth ponds of dust sitting in the bottoms of depressions like frozen puddles on a dead world. That shift, from abstraction to tangibility, from data to place, is perhaps the most important thing Near Shoemaker accomplished. It humanized the asteroid, not in the sense of making it less alien, but in the sense of making it part of our lived experience, part of our mental map of the cosmos. Eros is no longer just an entry in the Minor Planet Center database. It is a place that a machine from Earth has visited and touched. It is, in some small but genuine way, part of our world now, and that connection carries weight. Because if Eros is a place, a real place, with a surface and a history and a future, then the threats it represents are real too. The possibility, however remote, that Eros could one day impact Earth is not an abstract mathematical exercise. when you have seen photographs of its surface, when you have measured its mass, when you know the names of its craters and the texture of its regolith, the threat becomes tangible. It becomes something you can imagine, not as a disaster movie, but as a physical event, involving a physical object that you have studied and, in some sense, come to know. That is the dual legacy of Near Shoemaker: understanding and urgency, knowledge and vulnerability. The more we learn about asteroids, the more beautiful and scientifically valuable they become, and the more clearly we see the danger they pose. The two insights are inseparable. They are two sides of the same coin, and the coin was minted at Eros. The future of asteroid science will be shaped by both sides of that coin. On the scientific side, the data from Near Shoemaker combined with the sample return results from Hayabusa, Hayabusa 2 and OSIRIS-REx is driving a revolution in our understanding of the early solar system. We now know, with far greater certainty than we did before, what the original building blocks of the planets looked like, what they were made of, how they were processed, and how they were assembled. We know that water and organic molecules were present in the asteroidal material from the very beginning, raising the tantalizing possibility that the ingredients for life were delivered to Earth by impacts during the planet's earliest history. We know that space weathering is a real phenomenon that has been masking the true composition of asteroid surfaces for billions of years. We know that asteroids are not monolithic blocks of stone, but complex, fractured, structurally diverse bodies that range from shattered aggregates like Eros to loose rubble piles like Itokawa to diamond-shaped carbonaceous worlds like Ryugu. On the planetary defense side, the challenge is immense. We have catalogued most of the near-Earth asteroids larger than 1 kilometer, the ones capable of causing global catastrophe. But the catalogue is not complete. For the smaller ones, the city killers, the ones between 100 meters and 1 kilometer, we have found perhaps 40%. The rest are out there, unseen, unknown, orbiting in the dark. And even for the ones we have found, our ability to deflect them depends heavily on their physical properties. Their size, their mass, their internal structure, their composition, their spin rate, their shape. A strategy that works for a rubble pile may fail for a shattered aggregate. A strategy that works for a small body may be inadequate for a large one. Near Shoemaker showed us what one asteroid looks like inside. We need to know what many more look like before we can confidently say that we can protect ourselves. There is a strange irony in all of this. The asteroids that threaten us are also the asteroids that inform us. The same bodies that could end our civilization are the same bodies that tell us how our solar system was born, how our planet got its water, how the ingredients for life were distributed through the inner solar system. We need them, we fear them, we study them, we try to prepare for them, and we name them after gods of love. That naming convention deserves a moment's consideration, because it is not accidental and it is not trivial. When Gustav Witt named his discovery Eros after the Greek god of desire, he was following a tradition, naming celestial bodies after figures from mythology. But the specific choice was apt in ways he could not have anticipated. The surface features of Eros, named over a century later by the Near Shoemaker science team, all carry names drawn from the mythology and literature of love and desire. The great saddle-shaped depression where the spacecraft landed is called Hymeros, the Greek personification of longing. A prominent crater is named Psyche, the mortal woman loved by Eros in myth, whose name means soul. Another is called Cupid, the Roman equivalent of Eros himself. There is Narcissus. There is Don Quixote. There is Casanova and Lothario and Orpheus, the musician who descended into the underworld for love. The entire geography of this ancient, battered, airless rock is a map of human longing, etched into stone by committee and codified in astronomical databases. There is something both absurd and deeply fitting about that. We project our own stories onto worlds that have no stories of their own. We name craters after lovers and ridges after poets on a body that has never known warmth, never known water, never known the touch of anything softer than a micrometeorite. And yet the names stick. They become real. When scientists discuss the mineralogy of Hymeros or the boulder distribution near Psyche, they are using words that carry the weight of thousands of years of human emotional experience. to describe landscapes that predate ocean itself by billions of years. The naming is an act of colonization, not in the political sense, but in the cognitive sense. We make these alien places part of our mental world by draping them in our language, our myths, our stories. And in doing so, we bring them closer, we make them matter. The future missions, in development and under consideration, will extend this project of understanding in ways that the Near Shoemaker team could scarcely have imagined. The European Space Agency's Hera mission, launched in October of 2024, is headed for the Didymos-Dimorphos binary system to study the aftermath of NASA's DART impact in detail, measuring the precise change in Dimorphos's orbit, characterizing its interior structure, and advancing our understanding of kinetic deflection as a practical planetary defense technique. NASA's Psyche mission, launched in October of 2023, is en route to the asteroid 16 Psyche, a massive metallic body that may be the exposed iron-nickel core of a protoplanet that was stripped of its rocky mantle by catastrophic collisions in the early solar system. If that interpretation is correct, Psyche will offer a window into the kind of differentiated interior that the Earth has but that we can never directly access. Our own planet's core lies thousands of kilometers beneath our feet, unreachable by any drill ever built. Each new mission adds another layer to the understanding that began at Eros. Each one refines our picture of what asteroids are, how they formed, how they evolve, and how they interact with the planets that share their solar system. And each one brings us closer to the day when we will have to use that understanding, not for science, not for curiosity, not for the sheer joy of knowing, but for survival. The clock is running. It has been running since the solar system formed, and we are only now beginning to learn how to read it. So here is the answer to the question that has been hanging over this entire story. Why did we land on Eros? What did we find? And why does it matter? We landed on Eros because we had to know. For all of human history, asteroids were just points of light, faint dots drifting slowly against the fixed stars, too dim for the naked eye, too small for most telescopes, too far away for anything but mathematics and speculation. We named them, we tracked them, we calculated their orbits with ever-increasing precision. But we did not know them. We did not know what they looked like up close, what they were made of, how they held together, what stories they carried in their ancient minerals. Near Shoemaker changed that. Forever, what we found was a world, not a dead rock, not a featureless lump of stone tumbling mindlessly through the void. A world with craters and ridges and boulders and grooves and ponds of fine dust that nobody had predicted and nobody could fully explain. A world 34 kilometers long, tumbling end over end every 5 hours and 16 minutes, held together by nothing more than friction and the most gossamer-thin gravitational forces imaginable. A world that has survived for 4.56 billion years without fundamentally changing, while the planet we live on has remade itself 100 times over. A world made of the same elements that make up your bones, your blood, the neurons firing in your brain as you listen to these words. A world that carries, frozen in its minerals, the recipe for everything that exists, including you. We found that its craters told a story of violence, billions of years of bombardment, recorded in every scar and depression on its surface. We found that its interior was shattered but not separated, a fractured aggregate held together by mechanical interlock and the faintest gravitational embrace. We found that seismic shaking had erased the smallest craters and pooled fine dust into mysterious, glass-smooth ponds that defied easy explanation. We found grooves that recorded the moment Eros was nearly destroyed, the catastrophic impact that fractured it to its core and left wrinkles in its skin like scars on ancient bone. We found that its surface composition matched the ordinary chondrite meteorites that fall to Earth, confirming a connection that scientists had debated for 3 decades. And we found that sulfur was missing, a chemical anomaly that nobody has satisfactorily explained to this day. We found, in short, a body of staggering complexity hiding behind a facade of simplicity, an asteroid that looked like a potato and turned out to be a library. And in the final hours of the mission, we found something else entirely. We found that it was possible to land on a world no one had ever designed a spacecraft to land on. We found that human ingenuity could stretch beyond its intended limits and achieve things that had been considered impossible just months earlier. We found that a machine weighing less than a grand piano could be guided across 3 billion kilometers of vacuum and set down gently, at the speed of a slow walk, on the surface of a world where gravity is barely a whisper. And we found that the data collected during those 16 days on the surface, unplanned and improvised, would be among the most scientifically valuable of the entire mission. And why it matters is this: Eros is a reminder that the solar system is not finished with us, that the process of planetary formation, the colliding, the accreting, the scattering, the smashing, did not end 4 billion years ago. It is still happening. It is happening right now on timescales so vast that we cannot perceive it in a human lifetime, but so relentless that its consequences are, on geological timescales, inevitable. We live in a system full of leftover debris. Some of that debris carries the seeds of understanding. Some of it carries the potential for destruction, and we are only just beginning to tell the difference. The spacecraft that landed on Eros is still there. It will remain there for millions of years, far longer than any human civilization has lasted, far longer than our species has existed, possibly longer than any descendant species of ours will endure. It carries no plaque, no inscription, no golden record engraved with the sounds and images of Earth. Just instruments, a camera that has gone dark, sensors that have stopped sensing, a radio transmitter that fell silent on February 28th, 2001, and will never speak again, and somewhere within its small metallic body, a polycarbonate capsule containing a portion of the ashes of Eugene Shoemaker, the planetary geologist who spent his life studying impacts, who dreamed of going to space, and who finally reached another world only after he had left this one. A small metal body resting on the surface of an ancient stone body, carrying the remains of a human life within it, both of them circling the sun in an orbit that will carry them close to Earth and then far away, over and over and over, for eons to come. If some future civilization, human or otherwise, ever finds near Shoemaker on the surface of Eros, they will know one thing for certain. Someone was curious enough to build it. Someone cared enough to launch it. Someone was brave enough, or perhaps just stubborn enough, to guide it across 3 billion kilometers of emptiness and set it down, gently, improbably, on a rock named after love. Imagine for a moment that you could stand on the surface of Eros. Not that you could, in any practical sense. The gravity is so weak that every step would launch you into a long, lazy arc, and running would send you off the surface entirely, drifting into the blackness like a leaf released into the wind. But if you could somehow plant your feet and look up and shield your eyes against the unfiltered glare of the sun, smaller than it looks from Earth but still brilliant against the absolute black of space, you would see something extraordinary. Somewhere near that sun, in a direction that would change as the months passed and the orbits shifted, you would see a pale blue dot, barely visible, almost lost in the glare, but there, Earth, home, the only world we know of that took the same raw materials as Eros, the same silicon, the same iron, the same oxygen, the same carbon, the same hydrogen, the same trace of every element in the periodic table, and turned them into something alive, something that thinks, something that dreams and fears and wonders, and reaches out across the void to touch the places it cannot go. That is the story of Asteroid 433 Eros, an ancient rock older than the Earth that has drifted in silence since the solar system was young, a target for a mission that was never supposed to land, built by an agency that was learning to do more with less, guided by a team that refused to quit when everything went wrong, a scientific treasure trove that answered questions decades in the making and raised new ones that will take decades more to resolve. A reminder that we are made of the same materials as the cosmos we study, that the forces that built us can also destroy us, and that the line between understanding and vulnerability is thin and runs through the heart of everything we do in space. Eros orbits the Sun once every 643 days. It rotates once every 5 hours and 16 minutes. It weighs nearly 7 billion metric tons. It has been traveling through the darkness since before the Earth had oceans, since before life existed, since before the first star in our galaxy began to fade. And for 16 days in the late winter of 2001, it carried a passenger, a tiny robot from a distant world, resting on its surface like a message in a bottle thrown into the cosmic sea. Nobody will read the message. Nobody needs to. The act of sending it was enough. Somewhere out there right now, Eros is tumbling through the dark, and on its surface, in a smooth depression called Hymeros, a machine from Earth sits in perfect, permanent silence. It has nowhere to go. It has nothing left to say. It simply exists, a small, silent artifact of human curiosity, resting on a fragment of creation, circling the same star that warms your face when you step outside. That is enough. That is everything.